Above storm-churned skies, where thunderheads boil and dance, something stranger than lightning silently unfolds. High above the clouds, beyond the grasp of ordinary weather, immense red apparitions bloom like jellyfish in the upper atmosphere. These are not storms themselves but the atmospheric echoes of storms, massive, luminous discharges known as gigantic red sprites. They erupt upward from powerful thunderclouds, often triggered by unusually strong positive cloud-to-ground lightning strikes. And while they may last only a few milliseconds, their presence reaches tens of kilometers into the mesosphere, stretching with eerie grace like tendrils of plasma-colored ink diffusing through invisible space. Sprites are not new, but for centuries they were invisible to the human eye, whispered of only in rare pilot accounts or dismissed as illusions. It wasn't until the 1980s that scientists confirmed their existence with video footage. The scale was shocking. Some of these flashes tower up to 50 kilometers tall, dwarfing any structure on Earth. Unlike the blue-white jags of typical lightning, sprites glow in deep crimson hues, often branching like electrical coral or forming columnar pillars crowned with translucent domes called halos. Their color is a product of altitude. At such heights, typically 50 to 90 kilometers above ground, the atmosphere becomes thin and ion-rich. The red color arises as nitrogen molecules become excited by the electric fields, emitting light in the red portion of the spectrum as they relax. This is an environment more akin to the edge of space than to the weather we know. And yet, sprites are tethered to the planet's electrical heartbeat, intimately linked to storm systems far below. Sprites may appear chaotic, but they reveal a hidden structure in Earth's global electric circuit. When a thunderstorm releases a massive bolt of positive lightning, a rare type carrying more charge and traveling farther than its negative counterpart, it creates an electric imbalance in the ionosphere. The atmosphere responds like a stretched membrane snapping back into place, and a sprite erupts to restore equilibrium. This is not lightning as we know it, this is a plasma event, an electric bloom, a brief conversation between sky and space. What's extraordinary is that sprites might not be unique to Earth. Similar transient luminous events have been hinted at in Jupiter's and Saturn's atmospheres, suggesting that these ghostly flashes could be a common feature of planetary weather systems across the solar system. Studying them might give us clues not only about atmospheric electricity but also about habitability, radiation dynamics, and how energy moves vertically through atmospheres. They're notoriously hard to observe, too high for most weather instruments, too fleeting for the naked eye. But high-speed cameras, satellites, and even citizen scientists with low-light video gear have begun to pull sprites from the margins of mystery. Networks like the International Space Station's Lightning Imaging Sensor and the Japanese ISS instrument ASIM have captured their ghost-like geometries from orbit, allowing researchers to trace their timing, triggers, and altitude profiles with unprecedented clarity. And the more we study them, the stranger they appear. Sometimes, a sprite splits into dozens of parallel strands, cascading like an electric waterfall. Other times, it blooms into a mushroom-shaped burst with curling tendrils that pulse like a heartbeat. There are even rarer cousins, elves, blue jets, trolls, and goblins, each a flickering signature of electromagnetic energy breaking loose from the constraints of normal weather. Sprites remind us that the sky above is not just a passive canvas but an active layer of electrically charged matter. Their brief, silent dances tell us that storms are not confined to clouds and rain but reach into the edge of space, connecting the troposphere, stratosphere, and mesosphere in electric conversation. The atmosphere is not a collection of isolated layers but a continuum, a breathing, pulsing system whose patterns we are only beginning to decipher. They are delicate and colossal, ephemeral yet ancient, and their study draws us closer not just to understanding storms, but to understanding the boundary between Earth and space, a region where physics dances in plasma and silence. As technology evolves, so too does our ability to glimpse these fleeting phenomena with greater clarity. Ground-based observatories now use ultra-sensitive photometers and fast-frame imaging systems to dissect sprites frame by frame, revealing microstructures within the red filaments, subtleties that were previously lost in the blur of time. What seemed like simple tendrils of light are now understood to be composed of thousands of individual streamers, each a micro-discharge propagating through tenuous air with lightning-fast acceleration. These streamers, measuring mere meters in width but traveling at speeds approaching 1/10 the speed of light, exhibit behavior more familiar to laboratory plasma physics than to meteorology. They seem to pulse and bifurcate, forming clusters and branches like neurons firing in the brain of the sky. It's here, in this intersection of plasma physics and atmospheric dynamics, that sprites defy easy classification. They are part meteorology, part electromagnetism, part cosmic sculpture. What makes the gigantic red sprite even more captivating is its role as an emissary, an ambassador between the terrestrial and the celestial. When you see a sprite, if you're lucky enough, you're not witnessing a lightning bolt in the conventional sense, but the atmosphere's reaction to a sudden electrical demand from space. It's as if the sky briefly becomes a conductor, transmitting energy upward to rebalance a system stretched by the fury of storms. Each sprite, in its flash, is also a data point in Earth's global electric circuit, a planet-wide system of charge flow between the surface, clouds, and ionosphere. Thunderstorms act as batteries, pumping charge upward, while sprites and their kin serve as relief valves for extreme events. Understanding this circuit is vital not just for atmospheric science, but for comprehending how space weather interacts with our planet, influencing GPS, satellites, and even the health of astronauts. There is also a poetic tension in the way sprites remain at the edge of visibility, too high for most clouds, too low for auroras, too fast for casual observation. They dwell in the mesosphere, often called the ionosphere, for how little we have studied it. Yet here, in this neglected altitude, lies a crucible of dynamic forces, radiation belts, electric fields, plasma waves, that ripple and shimmer, waiting for the right trigger to ignite a sprite. As research expands, questions multiply. Why do sprites favor certain types of storms? What determines their shape? Why some form as simple vertical columns and others as sprawling jellyfish? Can we use them to remotely probe atmospheric conditions without balloons or rockets? And perhaps most intriguingly, do they leave lasting traces in the upper atmosphere, ionization trails, chemical shifts, or even electromagnetic echoes that ripple across regions we have yet to detect? From mountaintops and space stations, researchers continue to listen, to watch, and to wait. Every sprite recorded is another page in an unfolding cosmic diary, one written not in words but in light and charge. The more we study them, the more they whisper of hidden architectures in the sky, networks of energy we are only beginning to understand. Sprites, in their brief and brilliant lives, may also carry lessons about interconnectedness. That a storm, deep in a continent, can reach out and touch the very edge of space. That a single bolt of lightning can echo upward in a luminous bloom that spans the boundaries of weather and space physics. They are events of extraordinary delicacy and scale, bridging realms both literal and symbolic. And yet, despite all our instruments and theories, sprites retain a kind of wildness, an unpredictability that resists full domestication by science. Even when we can model the electric fields, anticipate the charge distributions, and align the cameras just right, the sprite still arrives like a cosmic improvisation, sudden, asymmetric, often asymmetrical, painting the mesosphere with strokes of crimson plasma that no algorithm can fully predict. In recent years, scientists have begun layering radio frequency data on top of optical observations. These combined datasets reveal that sprites are not just visual spectacles but emit complex electromagnetic signatures, brief bursts of very low frequency, VLF, and extremely low frequency, ELF, radio waves that ripple through Earth's atmosphere and beyond. These signals travel vast distances, interacting with the ionosphere, bouncing between hemispheres, and potentially influencing the behavior of charged particles in the radiation belts. In this way, sprites are not just witnesses of energy exchange, they are participants in shaping the electromagnetic environment of our planet. Interestingly, some researchers have proposed that sprites may even have subtle effects on atmospheric chemistry. The intense electrical fields and localized ionization could, in theory, contribute to the formation or destruction of transient compounds like nitric oxide or ozone in the upper atmosphere. While these effects are likely to be minor compared to global processes, they serve as yet another example of how dynamic and alive our atmosphere truly is, even in layers once thought inert and passive. But sprites are not merely the concern of physicists and atmospheric chemists. Artists, poets, and skywatchers have begun to embrace them as symbols of something deeper, a reminder that even in the most storm-tossed environments, beauty can arise from chaos, structure from turbulence, and light from hidden tension. Capturing a sprite on film has become a kind of pilgrimage for astrophotographers, who must wait in darkness near thunderstorms, with specialized cameras trained toward the invisible, hoping for a millisecond of wonder. And sometimes, a single frame contains an entire cathedral of light, a cathedral built from arcs, streamers, and spires that reach upward like prayers from the earth to the stars. From a philosophical point of view, sprites blur boundaries. They are liminal beings, inhabiting the threshold between weather and space, matter and plasma, science and myth. Their behavior is rooted in quantum-level particle collisions and macro-scale electric fields, yet the form they take resembles the branches of a tree, the neurons of a mind, the roots of some inverted lightning-born forest growing down from the edge of the void. In that sense, sprites are metaphors for emergence, complex patterns arising from the interplay of simple laws, flashing into existence with elegance and then dissolving just as quickly. They also challenge our sensory expectations. Lightning roars and cracks across the sky, sprites do not. They are utterly silent to human ears. You may see one and hear nothing. And that silence makes them feel otherworldly, like a secret performed in another language. You must translate their meaning through instruments and physics, but you feel it through awe. This quiet, momentary light connects us to an invisible realm of forces always at work just beyond perception. In that instant of red fire above the storm, the veil between Earth and space lifts. The planet breathes upward, and the heavens answer, not with thunder, but with flame. Physically, sprites emerge from the interplay of three critical systems: the thunderstorm below, the ionosphere above, and the mesospheric medium in between. When a large positive cloud-to-ground (CG) lightning discharge occurs, typically carrying currents of tens of kiloamperes, it removes a vast quantity of charge from the cloud top. This sudden shift in the electric field propagates upward at the speed of light, disturbing the quasi-electrostatic field between the thundercloud and the lower ionosphere. This altered electric field must meet a critical breakdown threshold in the mesosphere, where air density is sufficiently low to allow electrons to accelerate and multiply via avalanche ionization. The reduced neutral density at these altitudes increases the reduced electric field, E/N, a crucial parameter describing how efficiently electrons gain energy from the field relative to how often they collide with neutral molecules. At around 70 to 85 kilometers altitude, this ratio becomes optimal for triggering streamer formation, the slender plasma filaments that constitute the sprite structure. Streamer theory, borrowed from high-voltage laboratory discharges, explains much of what we observe. Streamers are self-propagating plasma channels that advance via electron multiplication at their tips. In the sprite context, upward and downward moving streamers form in clusters, sometimes with hundreds developing in parallel, leading to the familiar caret and column shapes seen in high-speed images. Laboratory simulations and fluid models show that these streamers propagate at velocities ranging from 10 to 10 cm/s and require background electric fields of several hundreds of volts per centimeter in the rarefied upper atmosphere. Interestingly, Sprite streamers are cold plasmas. Unlike lightning channels, where temperatures can reach 30,000 K, the electron temperature in Sprites may only be a few electron volts. 1 eV is almost equal to 11,600 K, and the ion and neutral temperatures remain close to ambient. The energy is concentrated in a small fraction of electrons, which gain sufficient velocity to ionize and excite atmospheric molecules, mostly nitrogen. The characteristic red light of Sprites comes from the first positive band system of molecular nitrogen, N21P, emitting strongly around 670 to 800 nanometers, with additional blue-violet contributions in the lower tendrils. Recent studies using time-resolved spectroscopy have resolved sub-millisecond transitions between excited states, confirming that Sprites evolved through a series of short-lived molecular interactions. The lifetime of the N21P state is on the order of nanoseconds, but because different streamer branches ignite sequentially, the whole event can last up to 10 to 20 milliseconds. Sophisticated modeling using the Poisson-Boltzmann equation, coupled with Monte Carlo simulations of electron transport, helps researchers understand the microphysical evolution of Sprites in 3 dimensions. Beyond the individual events, Sprites serve as real-time probes of the lower ionosphere, particularly the D region, around 60 to 90 kilometers, which is notoriously difficult to study due to its absorption of radio waves and inaccessibility to balloons and aircraft. When a Sprite occurs, it modifies the local electron density, creating transient ionospheric holes and perturbed regions detectable via VLF transmitter signals. This allows scientists to indirectly map the conductivity profile of the upper atmosphere and understand how space weather and solar activity modulate its behavior. Another scientific frontier involves the interaction between Sprites and gravity waves, oscillations in atmospheric density and pressure generated by storms, mountain ranges, or jet streams. Gravity waves can modulate the neutral background density in the mesosphere, influencing where and when Sprites can form. Some models even suggest that gravity waves can precondition regions of the sky, making them more or less receptive to electrical breakdown, effectively acting as invisible sculptors of Sprite geometry. In satellite data, Sprites often appear in concert with other transient luminous events, TLEs, such as blue jets, conical discharges erupting from thundercloud tops, and ELVs, rapidly expanding rings of optical emission produced by electromagnetic pulses, EMPs, that travel laterally at the speed of light. These TLEs occur at different altitudes, and together they form a vertical column of electrical phenomena that extends from the Earth's surface to the lower thermosphere, a system now understood as stratified electrical coupling. Through these studies, we've begun to appreciate that Sprites are not isolated events but are embedded in a complex electrodynamic ecosystem linking ground-level meteorology to ionospheric chemistry and even magnetospheric dynamics. The global electric circuit, once a theoretical abstraction, now takes on physical clarity through the lens of Sprites, revealing that every thunderstorm is not just local weather but a node in a planetary-scale electrical network. Laboratory experiments have become a powerful tool in advancing our understanding of Sprite physics. Although we cannot recreate a full-scale Sprite in the lab due to size and pressure differences, controlled experiments in low-pressure chambers using pulsed high-voltage systems have replicated the essential conditions of Sprite streamer formation. These experiments often use needle plane or point plane electrode geometries to simulate the intense local electric fields that form at the streamer tip, and they employ nitrogen-oxygen mixtures at pressures equivalent to the mesosphere, 0.1 to 1 torr. One key result from laboratory analogs is the validation of streamer scaling laws. According to similarity principles, the behavior of streamers, velocity, diameter, branching frequency, scales with the reduced electric field, E/n, meaning we can study mesospheric discharges by appropriately scaling down pressure and adjusting the driving voltage. Experiments have confirmed that streamer heads in Sprites propagate due to photoionization, where UV photons emitted from excited nitrogen molecules ahead of the streamer pre-ionize the medium, enabling continued growth in a low-density atmosphere. This non-local process is essential for sprite development, as it allows the plasma to advance into regions with insufficient background ionization. Computational models complement these experiments, using fluid, hybrid, and particle-in-cell (PIC) approaches to simulate sprite initiation and streamer propagation. Fluid models solve the coupled equations of motion for electrons and ions, along with Poisson's equation for electric potential, under mesospheric conditions. These models reveal instabilities at the streamer head, branching mechanisms, and charge deposition patterns. More advanced PIC simulations track individual particles, capturing kinetic effects such as electron energy distribution, secondary avalanches, and sheath dynamics. On a larger scale, global sprite climatology is now being mapped with satellite constellations such as NOAA's GOES-R, ESA's ASIM aboard the ISS, and the Chinese LAS/GLM sensors, which can detect lightning flashes and their associated optical transients. These data sets have enabled the correlation of sprite occurrence with mesoscale convective systems, MCSs, showing that sprites are more common over continental land masses, particularly in mid-latitude regions during summer. The most prolific sprite-producing storms are usually quasi-linear convective systems, QLCS, with sustained, long-duration lightning activity and strong charge separation. From these global datasets, researchers have derived statistical properties of sprites, their typical delay after apparent lightning stroke, 10-50 ms, altitude range, 50 to 90 km, horizontal span, 10 to 50 km, and optical intensity, up to several megarayleigh. A megarayleigh is an astronomical unit of brightness, and a sprite can briefly outshine the night sky background by orders of magnitude, though not enough to be easily seen without equipment. The connection between sprites and the Schumann resonances, natural resonant frequencies of Earth's electromagnetic cavity, about 7.8, 14, and 20 Hz, is another frontier of study. Some researchers propose that large-scale TLE activity modulates global resonance amplitudes, subtly altering the electromagnetic environment for days or weeks after large thunderstorm outbreaks. This connects sprites to broader questions in geophysics, such as the coupling of the lithosphere, atmosphere, ionosphere system and the potential for electromagnetic precursors to seismic events. There's even emerging interest in the biological implications of sprites and related phenomena. Though far above commercial flight altitudes, the electromagnetic pulses associated with sprites and TLEs could affect the local radiation environment in the mesosphere and lower thermosphere. Some theoretical work suggests that cosmic ray particles interacting with sprite-related fields may produce runaway electron avalanches or high-energy X-ray and gamma-ray emissions, part of what are now called terrestrial gamma-ray flashes, TGFs. These TGFs, detected by missions like NASA's Fermi Gamma-Ray Space Telescope, suggest that thunderstorms and associated phenomena like sprites may be among the most energetic natural particle accelerators on Earth. This positions sprites not only as spectacular optical displays, but also as critical agents in high-energy atmospheric physics. Their study overlaps with astrophysics, radiation physics, and even quantum electrodynamics. The Earth, it turns out, is not just a passive receiver of cosmic energy, it generates bursts of relativistic particles in its own sky, using thunderstorms as launch pads and sprites as signals. Planetary analogues of sprites open a new and thrilling dimension in the study of atmospheric electricity. If gigantic red sprites are the Earth's way of discharging extreme electrical tension between tropospheric storms and the ionosphere, then it is plausible that similar mechanisms may operate on other planets, especially those with thick atmospheres, convective cloud systems, and strong magnetic fields. Jupiter, for example, has the most powerful thunderstorms in the solar system. Observations by the Juno spacecraft have confirmed lightning at depths far below the ammonia cloud decks, with bolts potentially thousands of times more energetic than those on Earth. Juno's ultraviolet spectrometer has recorded flashes of light at altitudes far above these storm regions, flashes that resemble the hallmarks of transient luminous events, TLEs. These include rapid, upward propagating discharges with a spectral signature compatible with excited hydrogen, suggesting the presence of Jovian analogues to Sprites and ELVs. Unlike Earth, where Sprites arise primarily from molecular nitrogen emissions, Jupiter's upper atmosphere is dominated by hydrogen and helium, so any Jovian Sprite would likely appear as a blue or ultraviolet flash due to the different emission spectra of atomic and molecular hydrogen. This offers a new challenge: how to adapt Earth-based detection techniques, designed around nitrogen red emissions, to find Sprite-like events on gas giants with different chemistries and atmospheric pressures. Saturn, too, exhibits massive electrical activity. The Cassini mission detected persistent lightning storms in its equatorial belts, with flashes powerful enough to be seen from orbit for weeks at a time. While direct evidence for Sprites on Saturn remains elusive, models suggest that the enormous vertical extent of its atmosphere and ionosphere could allow for massive high-altitude discharges, possibly dwarfing Earth Sprites in size and energy. The ionospheric boundary on Saturn lies far above its cloud tops, offering an immense electric field potential and a large spark gap in which TLEs might form. Venus presents a different, more enigmatic case. Though its lightning is not yet definitively confirmed, electromagnetic anomalies recorded by Soviet Venera and later by ESA's Venus Express suggest possible thunderstorm activity within its thick sulfuric acid cloud layers. If Sprites do exist on Venus, they would need to propagate through an atmosphere dominated by CO2, with a dense and thermally layered stratification. Modeling shows that such discharges might produce a greenish or yellowish light due to emissions from CO2 and atomic oxygen, although the high background brightness of the Venusian atmosphere would make detection extremely difficult. Beyond our solar system, the study of Sprites may even intersect with exoplanet research. Brown dwarfs, objects between the mass of a planet and a star, show signs of powerful atmospheric storms and radio emissions that may be consistent with lightning and TLE-like phenomena. If Sprites exist there, they may occur in atmospheres composed of exotic molecules such as silicates, metals, or ammonia, emitting light in entirely unfamiliar spectral regions. Detecting such events could become a new method for remote sensing of alien atmospheres. Back on Earth, one of the most fascinating links between Sprites and high-energy physics comes from their association with relativistic runaway electron avalanches, RAs. Under strong electric fields in thunderstorms, electrons can be accelerated to near light speed if they avoid enough collisions. These high-energy electrons can produce X-rays and gamma rays as they collide with air molecules. This is the mechanism behind terrestrial gamma-ray flashes, TGFs, which were first discovered by NASA's BATS instrument in the 1990s. Sprites appear to correlate with TGFs in certain cases. Some models propose that the electric fields above thunderstorms, especially those that generate Sprites, may serve as secondary acceleration zones for upward-moving relativistic particles. In this sense, Sprites might serve as beacons not just of electrical breakdown but of high-energy particle acceleration, a role previously thought exclusive to astrophysical environments like pulsars and black hole jets. There is even speculation that such particle showers could have influenced Earth's atmospheric chemistry over geological timescales. During periods of intense storm activity or geomagnetic variation, the increased flux of gamma rays and secondary particles from thunderstorm-induced discharges could alter the production rates of nitrates and contribute to transient climatic effects. Although speculative, this idea opens a new interdisciplinary frontier connecting atmospheric electricity, climate science, and geochemistry. Sprites, therefore, sit at the nexus of many disciplines: electrodynamics, atmospheric science, quantum physics, astrophysics, and even planetary science. They are natural laboratories for studying breakdown processes in rarefied gases, mechanisms of plasma propagation, and energy transfer across layers of the atmosphere and beyond. They remind us that the boundary between Earth and space is not a wall, but a membrane, flexible, dynamic, and alive with processes we are only beginning to observe. At the quantum scale, Sprite streamers represent an exquisite example of how macroscopic electrical structures emerge from microscopic particle dynamics governed by probabilistic collisions, field interactions, and quantum excitation states. Though sprites stretch tens of kilometers in height, the processes driving them originate at the scale of nanometers, within the energy exchanges of individual electrons and molecules in a thin, partially ionized upper atmosphere. In a Sprite streamer, free electrons, seeded by cosmic rays, earlier lightning pulses, or photoionization, are accelerated by intense local electric fields. As they accelerate, they collide with neutral molecules, primarily N2 and O2. If the electric field exceeds the breakdown field, approximately 120 V/m at 70-80 km altitude, electrons can gain enough energy between collisions to ionize these molecules, releasing more electrons. This cascading chain reaction, electron impact ionization, is the foundation of avalanche breakdown, which underpins the streamer mechanism. But this is only part of the story. During these high-energy collisions, electrons also excite the rotational, vibrational, and electronic states of nitrogen molecules. These excited molecules then decay, emitting photons across the visible and near-infrared spectrum. The specific red hue of sprites is largely attributed to transitions in the first positive band system of molecular nitrogen, N2b superscript 3 pi_G A superscript 3 sigma_U, peaking around 670 to 800 nanometers. These transitions are quantum mechanical in nature and are governed by selection rules, oscillator strengths, and radiative lifetimes on the order of nanoseconds. Spectroscopic studies using high-speed instruments have captured the time evolution of these emissions, revealing how different excited states contribute to different parts of the sprite structure. For example, the tendrils in the lower portion of a sprite often show stronger emissions from the second positive band, C superscript 3 pi_U B superscript 3 pi_G, which appears more bluish and indicates higher electron energy densities. These fine-scale observations allow scientists to infer the reduced electric field, E/N, electron energy distribution functions, EEDFs, and the mean energy of the ionization-producing electrons, all essential parameters in plasma physics. In the streamer head, the narrow tip of the propagating plasma channel, the electric field can be amplified to 10 times the ambient value due to local space charge effects. Here, nonlinear electron kinetics dominate. The energy spectrum of electrons becomes highly skewed, allowing for rare but extremely energetic collisions that can produce ultraviolet photons, initiate photoionization far ahead of the streamer, and even generate low-yield Bremsstrahlung X-rays. These localized electron clouds also serve as sources of Cherenkov radiation, a phenomenon more often associated with particle detectors and nuclear reactors. Moreover, in high-altitude conditions, streamer propagation becomes increasingly influenced by non-local electron transport. Unlike in dense gases where collisions rapidly thermalize electrons, in the mesosphere, the mean free path can exceed several centimeters. This allows electrons to be guided by spatially extended electric fields, resulting in more complex streamer morphologies, spirals, forks, or simultaneous upward and downward growth. Such structures have been modeled using Boltzmann solvers and kinetic Monte Carlo simulations, bridging quantum-scale particle motion with observable mesoscale patterns. Interestingly, the sprite's interaction with the ionosphere can generate Whistler mode waves and Schumann resonances, extremely low frequency, ELF, electromagnetic waves that propagate globally through the Earth ionosphere waveguide. These signals, often detectable halfway across the globe, carry the electromagnetic fingerprint of a single sprite-producing lightning event. By analyzing the timing, frequency content, and amplitude of these signals, scientists can back-calculate the characteristics of the lightning discharge and the corresponding sprite. This global detectability has enormous implications. It means that sprites, though localized, participate in the dynamics of space weather, the study of how solar, atmospheric, and magnetospheric processes affect near-Earth space. For instance, during geomagnetic storms, variations in the Earth's magnetic field can alter the conductivity of the ionosphere, affecting sprite formation thresholds and altering the shape of the global electric circuit. In this way, sprites serve as indirect indicators of solar activity's terrestrial consequences. Some theories even suggest that the cumulative electromagnetic and particle output from sprite-producing storms could influence the distribution of trapped electrons in the Van Allen radiation belts. These belts, composed of energetic charged particles held in place by Earth's magnetic field, are sensitive to disturbances in the ionosphere. If sprites modulate the density of the D region, they may affect the reflection and propagation of plasmaspheric His and other wave modes that scatter belt electrons into the atmosphere. As this field matures, a unified theory of electrodynamic coupling is emerging, one that links the microphysics of streamer discharges with global circuits, planetary magnetospheres, and even cosmic ray modulation. Sprites, once dismissed as rare curiosities, are now seen as dynamic agents within a complex, multi-scale electrosphere, a region where chemistry, electricity, and plasma turbulence co-evolve in delicate balance. Detection and classification of sprites have undergone a revolution in recent decades, moving from serendipitous observations to precise, multi-instrument campaigns that combine optical, radio, and electromagnetic data from both ground-based and space-based platforms. This coordinated strategy allows researchers to not only capture sprites visually but also to triangulate their location, determine their altitude, classify their morphology, and infer the physical conditions that triggered them. From the ground, high-speed, low-light video cameras, often equipped with image intensifiers and narrowband filters, are mounted at observatories or mobile storm-chasing platforms. These systems typically operate at 10,000 to 100,000 frames per second, allowing them to resolve the temporal evolution of sprite streamers and their branching patterns. By using synchronized camera arrays separated by known distances, researchers can apply stereoscopic techniques to calculate the 3D geometry of a sprite with kilometer-level precision. In tandem, electromagnetic sensors detect the extremely low-frequency, ELF, and very low-frequency, VLF, waves produced by both the initiating lightning and the sprite itself. VLF receivers can be located hundreds to thousands of kilometers away from the source and still detect the signal due to its propagation within the Earth ionosphere waveguide. Time of arrival and direction-finding methods allow scientists to pinpoint the lightning stroke responsible for the sprite, while spectral analysis of the ELF/VLF waveforms provides information about current intensity and discharge polarity. At higher altitudes, satellite-based instruments like ASIM, Atmosphere, Space Interactions Monitor, and Tyrannies, tool for the analysis of radiations from lightnings and sprites, were designed to capture sprites from orbit. These instruments combine optical photometers, X-ray/gamma-ray detectors, and electric field antennas to study transient luminous events, TLEs, in their full electromagnetic context. Orbiting above thunderstorms, they offer a unique top-down perspective, crucial for studying the large-scale structure of sprite clusters and their relation to the underlying convective systems. With these tools, scientists have identified several distinct sprite morphologies, each reflecting subtle differences in atmospheric conditions, electric field configurations, and initiation mechanisms. Column sprites appear as narrow vertical channels extending tens of kilometers downward. They typically form first and mark the primary path of the downward propagating streamer front. Caret sprites are more complex, exhibiting a wide, bright top that narrows into multiple downward streamers. These are often associated with stronger electric fields and longer-lasting discharges. Jellyfish sprites are among the rarest and most magnificent, displaying wide, glowing heads with multiple tendrils that span over 40 kilometers horizontally. These usually occur during large mesoscale convective systems and may reflect enhanced ionospheric conductivity gradients. Angel sprites, a recently proposed category, appear bilaterally symmetrical with upward and downward streamers and may be linked to internal gravity waves shaping the mesospheric density field. These shapes are not merely aesthetic variations, they encode physical information. For example, the width of the upper halo can be used to estimate the vertical profile of ionospheric conductivity. The number and brightness of tendrils can indicate the magnitude of the parent lightning current. And the presence of upward streamers suggests complex charge motion near the ionosphere, possibly a sign of bidirectional discharge. Climatologically, sprites are more likely to occur over large land masses with intense summer thunderstorm activity. The central United States, South America's Gran Chaco region, the African Sahel, and parts of Southeast Asia are among the global hotspots. Seasonal maps show a strong correlation with the Intertropical Convergence Zone, ITCZ, and regions of high convective available potential energy, CAPE, suggesting that sprite activity is tightly coupled to deep convective weather systems. Statistical studies of sprite occurrence reveal several trends. Sprites are most commonly triggered by positive CG lightning, which accounts for less than 10% of all lightning strokes but carries a higher charge moment change. The likelihood of sprite production increases significantly when the charge moment change, CMC, exceeds 500 to 1000 km, a parameter representing the product of transferred charge and its vertical displacement. Sprites tend to cluster spatially and temporally during mesoscale convective system, MCS, life cycles, often forming near the rear flank stratiform region where intense positive lightning occurs. The occurrence of sprites increases during nocturnal hours, especially in the local post-midnight period. This is likely due to enhanced ionospheric transparency and reduced background light. Moreover, long-term sprite monitoring campaigns are beginning to uncover multi-year and possibly decadal trends that may be linked to solar cycles, ENSO, El Niño, southern oscillation, phases, and global temperature anomalies. If confirmed, this would make sprites valuable proxies for understanding deeper climate, electrodynamic coupling on Earth. Sprites, though brief, serve as fingerprints of extreme energy redistribution in the atmosphere. They form part of a dynamic cascade: thunderstorm lightning, electromagnetic pulse, mesospheric breakdown, chemical alteration, global circuit modulation. Every sprite is a localized event, yet a window into planetary scale systems. The connection between sprites and cosmic rays opens a compelling chapter in the interplay between Earth's atmosphere and the broader cosmos. High-energy cosmic rays, mostly protons and atomic nuclei from distant supernovae, quasars, or possibly more exotic extragalactic sources, continuously rain down on Earth, colliding with molecules in the upper atmosphere and creating showers of secondary particles, muons, pions, electrons, and gamma photons. These interactions are not just a passive background, they can actively seed the electrical conditions necessary for sprites. In the mesosphere, where sprites bloom, the air is tenuous and partially ionized, and local conductivity is highly sensitive to incoming ionization sources. When cosmic rays penetrate this region, they can deposit clusters of free electrons, so-called ionization trails, that lower the threshold for electrical breakdown. In this way, a sprite-producing electric field may succeed in forming a discharge only because a cosmic ray happened to pass through a critical volume microseconds earlier. Some models suggest that relativistic runaway electron avalanches, RRAs, triggered by both thunderstorm fields and cosmic ray seed electrons, may help launch sprites under borderline conditions. RREAs occur when ambient electric fields are strong enough to accelerate electrons faster than they lose energy through collisions, allowing a single high-energy electron to initiate a cascading particle storm. If such avalanches extend into the mesosphere, they could act as invisible fingers igniting the sprite's visible plasma. Research using ground-based cosmic ray detectors and synchronized sprite observation arrays has found statistical correlations between increased cosmic ray flux and higher sprite activity, particularly during periods of low geomagnetic shielding or solar minimum, when cosmic rays penetrate more deeply into the atmosphere. These findings suggest that sprites may, in some cases, act as magnifiers of the cosmos, turning invisible particles from distant galaxies into luminous events visible from Earth. This raises tantalizing questions about how sprites may influence, or even define, biospheric boundaries. The mesosphere and lower ionosphere form the upper envelope of Earth's life-supporting shell, separating living organisms from the high-energy radiation of space. While sprites are too rare and brief to directly affect life on the ground, their associated processes, ionization, electromagnetic pulses, chemical reactions, could have implications for airborne biology, including high-altitude microbial dispersal, viral nucleic acid stability, or the survival of extremophiles in the stratosphere and beyond. Some scientists have speculated that in Earth's early atmosphere, before the development of a thick ozone layer, sprite-like discharges may have been more frequent, more energetic, and more chemically influential. The mesosphere at that time may have been a kind of electrochemical crucible, where ultraviolet radiation, volcanic emissions, and high-energy discharges combined to generate complex organic molecules. In laboratory experiments that simulate prebiotic conditions, high-voltage plasma discharges in methane, ammonia, CO2, N2 mixtures, at pressures corresponding to ancient mesospheric levels, can synthesize amino acids, nucleobases, and other life precursor molecules. If natural sprites acted similarly, they may have contributed to the prebiotic synthesis of biomolecules long before the emergence of cellular life. This makes sprites not merely electrical curiosities but potential agents in life's origin story. On other worlds, this connection grows even more profound. Imagine an early Earth-like exoplanet with an active thunderstorm cycle, a weak magnetic field, and abundant atmospheric nitrogen. If such a planet also experiences frequent cosmic ray bombardment, especially from a nearby supernova or active galactic nucleus, its mesosphere could be a factory of plasma discharges and photochemistry. Sprites, alien yet familiar, might ignite there too, building molecular complexity in high-altitude realms beyond reach, offering a plausible path toward prebiotic chemistry in the absence of surface oceans or UV-irradiated ponds. From this perspective, sprites are more than weather, they are astrobiological phenomena, emergent structures that encode the interaction of planetary electricity, cosmic energy, and chemical potential. They represent how the universe, through storm and silence, sculpts complexity in the skies. Expanding into the realm of technological potential, sprites are increasingly recognized not only as objects of study, but as tools, natural sensors that can reveal hidden features of Earth's atmosphere, its ionospheric structure, and even incoming cosmic disturbances. These high-altitude discharges act like massive, transient electrodes, briefly illuminating and perturbing otherwise inaccessible regions of the atmosphere. In this way, sprites become diagnostic instruments, not constructed by humans, but sculpted by nature. Because sprites occur in the mesosphere and lower ionosphere, they provide real-time information about a part of the atmosphere that is notoriously difficult to study. Balloons cannot reach it, aircraft cannot fly there, and satellites often orbit too high to resolve fine-scale phenomena. But when a sprite occurs, it acts as a probe, disturbing the electron density and generating waves that ripple across surrounding altitudes. Scientists have learned to read these ripples, just as a seismologist reads tremors from distant earthquakes. For instance, VLF and ELF radio waves, generated or modulated by sprites, are reflected by the D region of the ionosphere. By measuring how these waves bounce and change, researchers can reconstruct the local electron density, temperature, and even chemical composition of the upper atmosphere. This technique is especially useful during solar flares, geomagnetic storms, or high-energy particle events, when the ionosphere is rapidly and unpredictably disturbed. Sprites can also serve as early indicators of space weather. Just as a lightning flash might foreshadow a growing storm, a spike in sprite activity, particularly in conjunction with blue jets or ELVs, may signal the arrival of magnetospheric disturbances, changes in global electric circuit behavior, or increased cosmic ray flux. By monitoring global sprite activity in near real time, space weather forecasters could gain new tools to anticipate changes in ionospheric reflectivity, satellite drag, or even ground-based technological risk. Another frontier of sprite-based diagnostics involves atmospheric gravity waves. These slow, oscillating waves are generated by imbalances in air masses, often caused by mountains, storms, or jet streams, and they propagate vertically, modulating air density in the upper atmosphere. Sprites appear to ride these invisible waves, sometimes clustering in specific regions where the background atmosphere has been preconditioned by density perturbations. By mapping sprite occurrence in relation to known gravity wave activity, researchers can indirectly study the global propagation of these waves, which play key roles in weather and climate systems. Sprites might even help us monitor anthropogenic influences on the atmosphere. As the climate warms and thunderstorms become more intense, the frequency and strength of lightning increases, particularly positive CG strikes, which are the main triggers for sprites. A statistically significant increase in sprite frequency over time could therefore act as a kind of planetary, vital sign, signaling shifts in global atmospheric energy balance and convective dynamics. On the technological horizon, there is growing interest in using cube satellites, CubeSats, to monitor sprites from low Earth orbit. These small, inexpensive platforms can carry photometers, high-speed imagers, and electromagnetic sensors, allowing a distributed network to capture sprite activity across the globe with unprecedented coverage. When coupled with ground-based camera arrays and VLF receiver networks, such a system could provide a global sprite tomography grid, a new way of mapping the dynamics of Earth's upper atmosphere in 4D, space, time, energy, and chemistry. Beyond Earth, sprites could also serve as probes of other planetary environments. Imagine orbiters around Jupiter or Venus equipped with sensitive light detectors and ELF antennas, tuned to detect transient optical and electromagnetic flashes in alien skies. A single confirmed sprite on another world would validate decades of theory and open a new channel of planetary diagnostics. Even without direct imagery, the spectral signatures of such discharges, brief emissions at known wavelengths, could act as fingerprints of atmospheric composition, pressure, or conductivity. In this way, sprites become not just subjects of awe or curiosity, but functional instruments in our expanding toolbox of space and atmospheric science. They offer a unique combination of vertical reach, electromagnetic breadth, and chemical impact, making them, arguably, one of the most powerful natural laboratories we have for studying high-altitude physics. Would you like the next section to explore future missions and AI-powered sprite detection, or venture into speculative theoretical physics, sprites as analogs for plasma processes in other astrophysical systems, such as jets from black holes or stellar coronae? And so, in the fleeting glow of a gigantic red sprite, we glimpse a vast and subtle dialogue, between earth and sky, matter and energy, chaos and form. These ghostly flames, born from storms but reaching toward space, are more than electrical ephemera. They are signatures of the planet's inner charge, markers of invisible architectures, and emissaries from a realm where weather dissolves into plasma and physics becomes poetry. Sprites remind us that even in the most ephemeral flashes, deep structures reveal themselves. They are born in silence, above the thunder, yet speak of forces that ripple across the globe and beyond. They record the breath of the planet, the influence of the cosmos, and the restless balance of energy that animates the atmosphere. To study them is to enter a domain where disciplines converge: electrodynamics, quantum mechanics, climate science, planetary exploration. To witness them is to realize that the sky is not empty, but alive. And to understand them is to know that the boundary between Earth and the universe is not fixed, but fluid, charged, reactive, luminous. Sprites are not just lightning's silent cousins. They are messengers. They are instruments. They are echoes of something greater. Fleeting, yet eternal in their meaning. A red signature on the dark canvas of the cosmos.